Hello everyone, I'm Paul and today we're solving problem 3607, power grid maintenance. This is an interesting medium, or at least it was for me. So let's start. We are given some number of stations or nodes and connections for these stations or edges. So as you can see, this is a graph problem. And here you can see the visual representation of this input. Now we are also given an array queries, and our job is to answer each of these and store each result in an array and return this. Now for each query we have two values. The first one is the type of query. If it's a 1, we are doing a maintenance check, and if it's a 2, station X goes offline. The second value in each query corresponds to X, meaning the ID for the corresponding station. For example, here we are doing a maintenance check on station number 3. Here, station 1 goes offline, okay? So the first element is the type, the second element is the station number or ID. Now, initially, every station is online. So let's start with this query. Here we go to station 3 and the query type is 1. We are doing a maintenance check. Now, if the current station is online, we return this, meaning 3. So we add 3 to the result. Now we are at this query. The query type is 2 and we are at station 1, meaning this station goes offline. And whenever we have a query of type 2, we don't add anything to the result. This stays as it is. Next we are here, so we are at station 1 and the query type is 1. Now this station is offline, and in this case we need to return the first station that's online and has the smallest ID. In this case 2. So we add 2 to the result. Now, let's say that every station here is offline and we run this query, for example. Given that every station is offline, we need to add a -1 to the result, okay? Now we are here, so station 2 goes offline. And given that this is an operation of type 2, the result stays as it is. Now we are here, so we are doing a maintenance check on station 2. And given that this is offline, we need to find the smallest ID for a station that's online. And this ID is 3, so we add 3 to the result. So for this input, we return this array. Now in this case, we only have one power grid, meaning one connected component. But it might be the case that we have more connected components. Now let's say that these two components are offline and we are running a maintenance check on this one. We can't just return 5 because these two components are not connected. Okay, so in this case we would add -1 to the result. This is very important. So my first intuition is we need to pre-process this somehow. And we need to store the information for each power grid, connected component, island, whatever you want to call this. We need to store the information for each of these somewhere. Let's say this is power grid number 1 and this is power grid number 2. And we also need to store the corresponding power grid for each node. So for example, we need to know where this node belongs to. In this case, node 2 belongs to power grid number 1. And this looks a lot like a map. Now, if we are doing a maintenance check on some station and it's offline, we need to be able to get the smallest ID of a station that's online in the same power grid. So, this is the power grid number 1. Maybe we can use another map where we are using the number of the power grid as a key and the value is a heap. And remember that the first element in the heap, meaning the head of the heap, is the smallest number. So we are building heaps of IDs. So in this map for power grids at 1, we are storing all of these nodes in this heap. And the last question here is, how do we deal with operation number 2? Let's say this node goes offline. The question is, should we remove this right away from the heap or not? And the answer is no, because if we ever need the smallest ID, we can just take the smallest ID, meaning we take the head of the heap, okay? Because this node is still online. Now, if at some point we remove this, we need to be able to check which nodes are offline and say while we have something in the heap and the current head is offline, we pop this from the heap. And for this, we can use a set. So when we are building this, at the same time, we are building another map where each key corresponds to the number of the power grid and the value is a set. And we are storing in this set all of these nodes. So when one node goes offline, we go to the corresponding set, meaning we go to this map at this power grid, meaning to this set, and remove this node. So next, when we are here, we are checking if the head of the heap is offline, meaning if the head of the heap is not in this set, we remove the head of the heap. So when this goes offline, we remove this from the heap because it's the head. Next, the head is this, and this is also offline. This is not in the set, so we also remove this. Next, we are here. This is the new head of the heap, and this is not offline. So if we need to return the smallest ID number, we know that the head of the heap is the smallest ID, okay? So with this information, let's see the full approach now. Let's say that we have this input. We have 3 stations and 2 connected components, okay? Here you can see the connections. We only have 1 and 2. And we are given these queries. Now we need to iterate every node starting from number 1. And here you can run a DFS or a BFS. In this case, we are running a DFS, but you can use BFS if you want. Now, we need to keep track of every node we see. For this, we can use a set. And given that we are here, we add number 1. Now, we need to add here to this map the corresponding ID. This is the key, and the value is the number of the power grid. We are currently at number 1, so here we put 1. Now here we are at power grid number 1, and remember here we are using a heap, and the first value that we are adding here is number 1. And we are doing the same in the form of sets. So for power grid number 1, we have a set which includes number 1 now. And we are running a DFS here, so we move to adjacent elements. Now we are here and do the same. Given that this is not in scene, we can add 2 here. And we add node number 2 corresponds to power grid number 1. And in power grid number 1, we need to add 2. And in power grid number 1 in set format, we add 2. So now we have seen every node in this connected component, and we can continue with 3. And we do the same, given that 3 is not in this set, we add 3. And given that this is a new connected component, here we add ID number 3 corresponds to power grid number 2. This is power grid number 1, this is power grid number 2. And regarding this map, we have power grid number 2, which has a new heap, and here we include number 3. And here we do the same in set format, so at power grid number 2, we have a set with 3. And now here we have all the information we need to answer each query. So let's start here. We know that ID number 2 corresponds to power grid number 1. So now we can go to power grid sets at power grid number 1 and check if here we have ID number 2, and we do. This means that station number 2 is online, and if we are doing a maintenance check and the station is online, we need to add this to the result. So we put the 2 here. Now we are at this query. Station number 2 goes offline. So we know that station number 2 corresponds to power grid number 1. So we can go to power grids in set format, add 1, and here we remove number 2, meaning this is now offline. And remember that for operations of type 2, we don't add anything to the result. Now we are here, we need to do another maintenance check on station number 2. We know that station number 2 corresponds to power grid number 1. We go to the corresponding set, and here we don't have a 2. So we need to find the smallest ID in the same station that's online. So we can go to this power station here, and here we have an array with 2 values. This is offline, but it's still in the heap. But actually, we don't care because we only care about the head of the heap, meaning this. We need to return the smallest ID. So we can just take the head and add this to the result. Now let's go with this query. Station number 3 goes offline. We know that station number 3 corresponds to power grid number 2, so we go to the corresponding set here. And this goes offline, so we remove this from the set. And given that the operation type is 2, the result stays as it is. Now we are here, we are doing a maintenance check on station number 3. We know that this station corresponds to power grid number 2, so we go to the corresponding set here and check if 3 is online. And we don't have 3 here, so we go to the corresponding heap and we are checking if we have this head in the corresponding station in set format, and we don't have 3 here. So we need to pop this, and given that this is now empty, we need to add -1 to the result. Finally, we return this. So this is the entire approach. First, we pre-process all the information and then we can answer queries. So with this in mind, let's go with the code. Here we need to do 2 things. First, pre-process power grids and then build result. So let's start up here. First, we need an adjacency list. And this is very important for DFS and BFS. Remember that here we are implementing a DFS. So this is a default dictionary with a default value of an empty array for every key. That's why here we use the word list. Now for AB in connections, adjacency at A dot append B and adjacency at B dot append A. So now we can build our DFS function, and this takes an ID and some ID of a power grid. We are calling this power grid ID. First, we add to scene the current ID. We'll have a set which is scene, and next we need to add node to power grid. Next, we need to associate power grid number with node, and then we can say for every neighbor in adjacency list at ID, if neighbor not in scene, we run a DFS with the neighbor and power grid ID. Now for this we will have an array which we'll call power grid PG, and here we can append the current ID, and for this part we will have a map. Remember the approach. We'll call this ID PG at the current ID is equal to power grid ID. So now we have our DFS, and we will have a set. This is to store every node. Remember the approach. We have a map, which is ID PG. This is an empty map. Sorry, this is ID. We have another map for power grids. Remember that here we are storing heaps, and we have the same in set format, pgs underscore s. This is an empty map, and we have power grid ID, which is initially 1. This is the number of the current connected component. We start from 1. And now we can run this DFS. So we say for every ID in range from 1 to C plus 1, because C is included. First we check if ID in scene continue, else we have a new island or power grid or connected component. So first, this is an empty array. Next we can run the DFS with the current ID and the ID for the power grid. And now we can say power grids underscore s at this power grid ID is set from the current power grid. Remember, after we run this, we will have some elements here. Now, we also need the corresponding information for the other map. So here we can say heap q, heap phi, power grid. So now pg is a heap, and we can say pgs at pgid is the new heap, and now power grid id plus equal 1 for the next connected component. Okay, and now we have all the information to build the result. This is initially an empty array, and for every type and ID in queries, power grid index is ID power grid at ID, power grid set is pgs underscore s at the current power grid index, power grid heap is pgs at the current power grid index. So now we can say if the type is 1, meaning we are doing a maintenance check on the current station, we say if we have the ID in power grid set, we add to the result the current ID. Else, we need to add to the result the smallest ID that's online and it's in the same power grid. Remember the approach. So here we can say if power grid heap, if we have something in the heap, result.append power grid heap at 0, meaning the head of the heap, meaning the smallest number. Else the heap is empty, so we add -1. And before this, it might be the case that the head of the heap is offline. Remember the approach. So if so, we need to remove the head until the head is online or until the heap is empty. So while we have something in the heap and not pg heap 0 in pg set heap q heap pop from pg heap. Okay, now if t is true, we say if we have the current ID in pg set, pg set dot remove the current ID. This is exactly the same we did in the visual approach. Okay, finally we can return result. So this is the entire code. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Here we have about 50 lines of code, so this is a pretty long code. And regarding time complexity, for this first part, it's big O of the amount of nodes plus the amount of edges. And maybe you are wondering why if we are running a DFS for every node. And the answer is we have a set to keep track of the nodes that we have already seen. That's why. So that's the overall time complexity for this part. And regarding this part, it's big O of Q for queries times log n. Each of these operations in the heap requires log n time complexity. So overall time complexity will be big O of n plus m plus q log n. And space complexity is big O of n plus m plus q. Okay? So this is it for this problem. If you found this useful, drop a like, subscribe, and see you in the next one. Bye bye.